But like, what I think is making it fascinating is the emotional power, and then we're trying to translate this, I do test it reports, is another one of the ball.
All right, we should get started.
Yeah. I think it's all about it, it's cheaper.
So through talking to people in office hours, I've come to conclude that I have not gone over iterators and motivated them to the extent that I probably should. So we're gonna spend just a few minutes motivating them, talking about their use, and then we're gonna go back and finish and test the one we have written. And then I think we're finally ready to move past at least the in-class portion of designing this linked list. So the motivation is something that I've basically motivated, but I haven't really done a good technical job of talking about it. So the purpose of one is if you're going to modify some kind of collection while you're looping through it, we're writing a kind of list. So if you would want to add or remove to the list while we are in the process of looping through it. So what can arise? The next index we want to do if we delete the current element. That is the first thing that I kind of want to draw out so that we can visualize exactly what this looks like. Let's give us a linked list of size. What is the next thing we're going to do? I'm going to do it over here. Okay. Linked list size for index 0, 1, 2, and 3. Let's say we want to remove index 1. So we want to do something that gets rid of this node. We want to delete that node. What is the next index that we would want to consider? So we would have parsed this, said, is this the node we want to remove? No. This node, is this the node we want to remove? Yes. What is the equivalent? Let's actually put values in here. Let's put in, I don't know, 10, 11, 12, and 13. The end result of what we want here is we want a list that has 3 elements. We want them to have 10, 12, and 13 at index 0, 1, and 2 respectively. So after we've gone through that remove, we want to convert top list into bottom list. After this is done, what is the next node to consider as we are looping through this? What is the next index? Yeah?
The third. So while we're looping, you're looping.
Yeah, so think of it as we're taking this concept. We've written this as a for each type of loop. So for each node in our list, this gets converted behind the scenes into a for loop that's going to say start a counting variable at 0, go well less than the length of the list. The issue is after we remove, the length of the list has changed, which is fine. It's just that let's actually draw this out. So if we were doing this as a for loop, which the for each loop actually is using an iterator underneath the hood, but let's say for the moment that it's creating a for loop so that we can see this issue. We would say we just do something for each one of this. Maybe we print out the value, but we have some condition that says if we reach index 1, we're going to delete that. If the current query is index 1, delete it. Or if the current value is 11, delete it. We just want to remove all 11s from this list. Any of those would work to show this. So we go through this and we handle this first node. Maybe we just say print the value of the node, but if the value of the node is 11, delete it. So start out I at 0. We're going to come into the loop and we're going to print out the value of that node since it is not 11. So we would print out and see 10 to the screen. Bump up I is now 1, looping around. We can now see at index 1 of this list, we have 11, great. But 11 is what we want to remove. So we're going to go through that process And we're going to convert this to this, which is what our remove does. Great, we handled it. Bumping up I is now 2, looping around. What is the node we're actually looking at? Yeah,
The one with 13, that's the
one with 13 in it. We skipped over this node because it is now at index 1. There used to be something at index 1, but because we bumped up I, we're looking at the incorrect index. So we're not actually looking at every node in this linked list. If this didn't happen to be 12, this happened to be 11, you can now see how that bug would arise. We would be looping through the list and we would fail to catch one of the nodes that is 11. And if we were printing this, we would now see 10, 11. Because we would have deleted this and now passed over it. If we were after this whole process completed, 10, 11, 13 would be what's in the list at the end of that process. We wouldn't have correctly removed every 11 from the list. Even though when we print it as we're doing it, it looks like, oh, 10, 13, we did it, we removed every 11. And then after that fact, you go back and look at your list and there's still an 11 there. That could be a pretty difficult bug to figure out and understand why it is happening. So the reason we use an iterator is to handle this underlying logic of when we add and remove in the middle of this process, we need to reset our expectations of where we are in the list. So we make sure we're not skipping over something if we remove or duplicating something if we add. We get the opposite problem if we go try to add. Why did they do this to me? Put the eraser as far in the classroom as possible. Questions on that? Any concerns with the motivation of why we need an iterator? Again, we don't have to make one, but if we fail to make one, then we can't state that our list is iterable with modifications, which we might, that's some functionality we might want to make sure is present in anything that we do. So we need extra logic. These do exist, they're built in for us. I just want to show you how they work so that if you need to make one for your own object type, if you're going to make a collection in the future, then an iterator will be provided for you. If you import anything from the Java library, it has an iterator built in. So you import a linked list from the Java library, has an iterator. Any collection type is going to have an iterator. So everything that's built in, you can call that particular object .iterator, and that is a constructor for an iterator for that object. So you instantiate a linked list. Let's call it list. You can say list.iterator, and that returns an iterator object. So you would get something like this. You would just say iterator, whatever you want to call that variable name. Historically, Java developers have called iterator variables it, but you can name it whatever you want. And you just say list, the name of the list that we made, .iterator, and that returns that iterator. Now you can use that IT, you can say it.hasNext, it.next, it.add, or it.remove in order to do anything that the iterator would do to that list, because it is now connected to that list object. And you see that when we say list.iterator, it makes that connection. This is an iterator for exactly that list and only that list. So the methods we've written or would need to write if we were doing this in general, we have a hasNext. It's just going to tell us whether there is another element in the collection. The only time it returns false is if there is a last element of the collection and you are at that last element. Next returns something of a generic type. And again, I wrote this a while ago, so I'm using E here. We would be using T for our example, but it returns something generic. It'll actually return the next element in the collection. Note that it's really important to call hasNext before you call next. If you assume there is a next and there is no next, then you may get some kind of no pointer exception. You're actually trying to dereference null. We try to catch this. So a no such element exception if there is no next element, rather than just crashing. And rather than saying, we have a null pointer exception, you can use a no such element exception to be more specific about you're trying to return an object. There is no object. No such element exception. That is true for any method that's going to return a generic type like that. You can do that when there is no such element. We want to remove. The trick to remove is that remove attaches itself to a node that says right now, if we wanted to remove, this is the node that we would go remove. Once we remove, we're going to detach that pointer. And now we have to call next before we try to remove again. And the reason for this is if we try to remove and then remove, we don't necessarily have that at the place where we want it to be. We're going to, we saw this last time when we implemented it, attach it to the previous object and follow its next reference for a linked list. And the reason is we don't know where that previous next points now. It could be that it doesn't point where we would assume that it points. So we're going to go back to it and follow it in case it is detached from whatever it is that we expect. So remove throws an illegal state exception if remove is called after remove or remove is called before the very first next in order to attach that pointer of what we're going to remove to some node in the list. So we have to call next before remove, and then at some point we have to call next before we remove again. If you violate that, that's what triggers the illegal state exception that we wrote yesterday. So making sure to call has next before assuming there's a next. Just make sure that you never throw an exception, even though we do handle that exceptions case. And then if you are iterating through any kind of collection rather than using a for each loop, you should use an iterator moving forward. That is the entire purpose of this type of object. So now that you know that it exists, you know what is involved in one, how to make one. If you are making changes to a loop, add to a collection as you're looping through it, use an iterator. Questions on what they are, why we care to use them? Any motivation, any of the how-tos? All right, well, we are almost done with this. So we're gonna hop right back to the code. And we're gonna finish up this. So let's go over the remove again, just because I think with that, it's worth going through what we did. We said it's going to throw that illegal state exception. That's going to say we can't remove if we've already removed. And this is why it's important for pause to be null when we call next. If we're going to call next, we've just removed that pause is pointing at the node that we would want to remove if we are going to remove. So if we have removed, we set, this pause ends up being set to something that ends up being null when you do that. Let's go ahead and write the add. So if we want to add in the middle of a list, all we need to so if we're going to add, we add at the current position. We don't need to provide any index. We don't allow for adding at any point. If we were going to do that, we should be just using the lists add. This is the iterator's add that says we want to add at the current position we are iterating. So because of this, we only need the data that we want to add at that location. So implementation, we just first want to check whether the head is null, because if the head is null, we're going to dereference null if we try to assume it has a next or it has a value, if we wanted to figure that out. So we are first going to Let's make the node first, actually. Call this, this is going to be the node that stores this value of data. Since that doesn't exist currently in the list, we need to actually construct it. Not the list, this node.
Bottom five and simulating.
I did.
Well, it's not throwing anything.
Not throw anything.
Not throwing exceptions.
Yeah, and there's nothing really that can go wrong in the add. Even if the list is empty. We try to add to an empty list, it's going to be the only element in the list. There's nothing that, I mean, even if data could be, we could check for null. And fail to add null. Well, I guess we could do that. Word our legal argument exception. So add is not required in an iterator. We are putting the add in there as an optional. But in order to actually implement this iterator only expects a has next, a next, and a remove. That doesn't mean you can't add additional functionality, but we want to be able to add in the middle of our list as well, and not just remove. So now that we have our node, we can check if the head is null. Then we want to set that to be the new node that we made. And that's going to be the only node in the list. Great. We have successfully added it in the case that the list was empty. Now we need to check if the current node that we are pointing to, if that is null. So if that's not null, then we can just mess with and dereference its next. So if this is not null, we can say this, the node that we just made next is going to point to wherever our current node points dot next. So we're making a connection between the node we just made next and the current node that we are on next. So we're going to make that connection so that we can now modify pauses next to point to the new node. I'm actually going to factor this out because this is something we're going to do regardless, but the next line of this would be to say that pause dot next is the new node that we created. This, just like when we drew the add diagram before, is going to add at that position. It's the exact same logic as adding at a position in the list. It's just that instead of one of the fields of the list, we're using a field of the iterator, the current node we are on in the iteration. If pause.next is null, what does that tell us? We're at the tail, yeah. So you just have to make sure we change the tail because we're making this connection pointing to the new node. Regardless of what we've done, since we didn't call any of the add methods in our list, we've modified the size of the list. So we need to make that associated change. And this doesn't return anything, so we should be done at this point. We have added at that position. Yes,
In the second if statement, where you know it's headers null, we're adding just a single node.
yeah,
Do we have to assign it to tail as well, or is that just one node?
that is a great question. We probably do need to assign it to tail as well. If the head was null, then I think that's a good point. That doesn't happen for us in our linked list to the best of my knowledge. Yeah,
And then, in the remove method, do we also have to take care of the tail in case we're removing? The
yeah,
list?
we're removing the tail here. So if the current node that we are removing is the tail, then we would need some kind of, where we've identified the previous. Yeah, we probably need to do that as well. I'll do that really quickly offline before I throw that up, just to make absolutely sure that that is right and valid. But let's go ahead and write a driver real quick. Just to be able to test things. So if we wanted to write a driver for this and really test the functionality, there's a lot that we could do. And there's a lot that we should do if we want to ship this knowing that it 100% works. We go over this a lot in software engineering. What kinds of tests do you need to write to be reasonably sure that something works? Given that you have a limited amount of time and a limited amount of development effort, how do you target tests that are going to reveal bugs? For now, I'm just gonna write a driver, and we're going to assume that if this driver works, then our system works. And if there are issues, I will go fix them offline before I upload the code, and we'll talk about it in class exactly what I did. I don't think there should be anything that's too crazy. So we are going to write a main inside of our driver because this is the starting point. If we are going to run this list, this is going to be the kind of a list tester. So the first thing we should probably do is make a list. We now need to define the type of this list. We can't use a generic inside of a main. So we are going to make doubles. The reason we use capital D double is that for any generic type, you need to give it an object. If you want to give it a primitive, you need to use one of Java's built-in wrapper classes. This is one of those. Do we know too much about the wrapper classes? Have I asked that question in here yet? We're going to talk about it really briefly because this is an aside that is quite useful. So a double, a primitive double, is going to store just its value. That is the extent of the data that is contained within this field. So we're going to say this is 3.14. Why not? First few digits of pi. If we want to show this representation in memory, how a double is stored in memory is you have a component where we basically break this and we're going to have some digits. And we're going to have some exponentiation. So stored in here would be 314, and stored in here would be the times 10 to the something that's going to move that decimal place one way or the other. So this is why we have a certain level of precision. This is why we get rounding errors, because we have a finite amount of storage for this. But the entirety of this takes up 8 bytes. And that's going to store everything that we would care to store. A float is just the same thing as a double, but it has about half the precision. So doubles take twice the memory, give you a lot more precision, make it harder to make compounding, rounding errors. But that is the extent of a primitive double. The capital D double is an actual class. And if we want to break down what a class is, we break it into two components. It's fields and its methods. I call this the state and the behavior. So the state of a double is really just this value, right? So one of the fields of this object is a primitive, whatever we want to call it, the actual value of what we're trying to store. But because we encapsulate this inside of an object, it allows us to write methods for how we handle this. So this allows us to determine, for instance, if a double is nan, not a number. You try to divide by 0. You try to just do any mathematical operation that is not allowed. What is the internal state representation of this double? You will see that there are some values. These are things you can call that set this double to either nan or infinity or something else that can't be represented within this structure. You can't represent the concept of infinity with some digits and an exponentiation. You can only represent it as here is a value that just happens to represent infinity. When you see it, infinity is the result. Not a number is the result. So using an object, you can actually incorporate more behavior into that object. And since we are expecting a generic type inside of this linked list, we're expecting an object, then we can pass in this kind of object, but not this kind of primitive. So if we want to represent this inside of a list, we're just going to use this and really just treat it like none of the other stuff exists except for this internal single field that represents the value of the double. So here's how we how do we want to say that? I don't want to use objectify because it's not what we're doing, but it would be funny if we did. So we're objectifying a double. And only being able to use it in its class, in its class form. Questions on that concept? That's true for every primitive type in Java as well. So you can do this to an int. There's an integer class that does exactly the same thing. If you ever wanted to know the largest possible value that an integer can store, does anyone have that memorized? Does anyone know an approximation for the largest value an integer can store? Yeah?
It's between -2 billion and 2 billion.
Yeah, 2 point something billion.
Yeah.
How do we know what that value is? Well, we know that there are in general 32 bits that we use for an integer. And one of those is going to be put aside to be, we want to represent both positive integers and negative integers. So we only want to be able to go up to 2 to the 31st positive and 2 to the 31st negative. And that gives us the window of legal integers. So you could have that memorized, or you could just call integer.max value, and now you don't have to have it memorized. It is one of the fields of the integer object. Is hard-coded stored, this is the largest value that this can store. You also have min value, the smallest value that this could store. So again, wrapping this inside of a class allows you to have that kind of structure and allow you to create additional pieces of information that relate to this object type that can be referenced by a name rather than knowing the value or memorizing the value. Yeah.
Are little things like this basically used to prevent people from putting in numbers that they shouldn't be able to put in? Like,
The behavior is never specified. You can always try to put in a larger integer. Does anyone know what happens if you try to put in a larger integer value? If you're using the class, that exists.
Yeah.
You can check for that. If you're using the int, it wraps around. Has anyone ever, have you seen a binary representation in two's complement of positive and negative numbers? Is that something you've seen before? Another random thing I like drawing out in order to visualize why that is. What is the rule that you have memorized for converting a positive to a negative or a negative to a positive in two's complement? Flip the bits and add one. That works all the time, right? If you want to go from a positive number to a negative number, flip the bits, add one. If you want to go from a negative number to a positive number, flip the bits and add one again. Shouldn't we flip the bits and subtract one? Why do we add one both times? Does anyone have any intuition for why that is, or is it something that you've memorized? I'm going to draw real quick a small two's complement system. And up top, we're going to have 0. Here we're going to have 1. Here we're going to have 2. Here we're going to have 3. What is the actual representation of -1 in binary? Yeah.
1 0 1.
It is all ones. All ones. So basically, I'm saying that this process is going to increase the value of this system that is only going to represent, going to use 2 bits to be able to represent between some kind of +3 and -3. So not particularly useful. Down here, I'm going to have the opposite. I'm going to have the -1. And I'm going to decrement 1 each time I move. So this is going to be 1 1 0. This is going to be 1 0 1, and this is going to be 1 0 0. Now we're going to represent what all of these are in binary. So here we have the decimal 0, the decimal 1, the decimal 2, the decimal 3, the decimal -1, -2, -3, and -4. Since we don't have a positive and -0, we can represent one more positive or negative number than the other. So we can see that this goes from 3 up to -4 because we have that middle point 0. So now, if we want to convert between a positive number and a negative number, where is that according to this? This is also moving in the positive direction. So we wanted to convert 1 to -1. We go straight across and then add 1 by the direction of this add to get us to -1. We want to go back to +1. We go straight across and we add 1. And that's true for any position on this radial that is not getting from 0 to 0. Or from getting from -4 to +4. Because neither of those exist. But for every other positive and negative number, it allows you to be able to visualize exactly why this process works. And it's because 1 1 1 is -1, and as you subtract 1 from, if you were to envision this as a 3-bit binary number, and you see that this is adding in both of these directions, that's why the adding 1 works, creates this little hourglass figure in the middle every time you try to flip back and forth between inverting a positive to a negative and back to a positive. So I just like drawing that out because it helps us to see why that is. Total aside, but it's a fun one. So now that we are inside of this, we know that we're going to be making a list of doubles. We'll call this our list. We'll call our constructor. I have to specify it here, I don't think we do. We gotta import. Yeah, I missed the new, didn't I? You know, it's gonna be a long day when you make basic mistakes early on. So let's go ahead and first print out the list as it is. This should be an empty list. We shouldn't see anything except for that open and close curly braces. So if we run this and we see that, we do get, in fact, our empty list, nothing in it. Question?
What comes out if you just do system layout list?
If we do the list, that's going to give us the location of the list in memory. Unless there is something that is overloaded, so you're going to get something that looks like it actually does know to use that list.toString. If we didn't do that, then frequent behavior in this, if you haven't defined exactly what printing out the list is going to do, is it's going to give us the actual location of it. So if we go into our singly linked list, and I'm actually just going to quickly comment out our toString. To demonstrate that behavior. So we comment that out. We go back to our driver. We run this on that, and we see that we no longer get something that makes sense, something that you've probably seen before. Yeah.
Question, how would you comment on rows?
Usually that's something like control/ over something that's highlighted, and that can, like, there's a block highlighted. Block.
It's Control A.
Yeah.
Where does it define, prior when you didn't have that comment out, that printing out just list by itself would use toString?
That is embedded within Java, its rule. If a toString is done and you try to print something, it's going to look for the toString. If the toString exists, it'll use the toString.
Okay.
If the toString is not defined for this particular object, then it will use the reference variable. So we know that we've created, when we make this list, it's not actually a list.
Right.
It's a reference variable. This is our list. And right now, it points to nothing before we instantiate it and do, when we say new singly linked list, this actually makes the class. Even though it calls the constructor, it does very little, not much of that list does anything. But now this references here. Rather than printing out, since there's no toString, how do we print out this object? It's not defined. So the most likely thing you're asking for is, where is this? In this long memory that is all of the memory in our computer, where is this? So this is a hexadecimal representation of a memory address where this object is stored. Useful if you're able to do something with it, which you are in a language like C or C++ that actually allows you to manage your memory and uses real pointer values, real pointer variables that are manipulable. But in Java, a reference variable is set and you can't modify it. So because of that, we can't do anything with this address. We can't move it to a new location from within our code, but yeah, it's because we implemented the toString. If you're trying to call the toString, I always prefer to see the .toString there. It just makes it a little bit clearer. So I'm going to leave it like this. If it compiles and works, there's nothing wrong with it. So let's go ahead and call some methods. We're going to call add, and we're going to add 1.0. We are going to call add and give it 2.0. We're going to add 3.0. And now we're going to print out the list again. That. And we see that I have not correctly added spaces in my in my list print, but here we have some values. Let's actually go fix that because we're currently looking at it. In our toString, when we're inside of this loop, we just want to add a space at the end of that and not one at the end here. That should fix everything inside of our driver. Now everything in the middle is separated by a space. Should have been there in the first place. Now we can start doing some fun things. Let's see what we want to do. What happens if we try to remove let's say, what remove do we want to call? We want to call remove on an index, or do we want to call remove on a value?
Index.
On an index, let's remove the first element and now see if this works correctly. And again, I'm just playing around with this. The better way to do this is to write a bunch of unit tests and ensure that that functionality is always there. It's not usually worth it to write a driver and test with a driver. It is best to write a series of tests. You actually have a test harness. And then something we'll talk about in software engineering, you want to attach that test harness to the actual process of developing the application so that you know every test that you have written is always working, regardless of any changes that you or anyone else makes. But for the moment, I'm just going to go through and test in a driver because it allows us to see what's happening and look at what's happening. Later on, we can talk about some tests. If we wanted to remove a particular value, let's say we want to look for 2.0 now instead of the actual value. We want to remove the first instance of 2.0 in the list. You see that works successfully. So I'm at least reasonably sure there are tons of side cases. I haven't tested anything about removing the tail. I haven't actually looked at where the tail points when I do this. But I also wanted to look at how do we make an iterator and use the iterator's logic. So before removing something, we're just going to have this list of 3 elements. How do we make an iterator for this? We could say we're going to make a list iterator, which is what we called it. And it also takes a type. Since we want this iterator to be over this list, we have to feed it the same type. So we're going to feed it double. We're going to call it it. And we're going to construct this, which of course we haven't implemented. This doesn't come default with any iterator that you make. Inside of our list, now we have to go back and write the ability to construct that iterator. So back in our singly linked list, let's go look at writing an iterator constructor. Let's see, let's do that. It's at the very bottom. It doesn't have to do with this list itself. So inside of this, we want to be actually writing very easy. It's a single line. Since this is inside of the list, it's going to be generic. We call it iterator.
Do we have to have a return type?
You probably do have to have a return type, except that it's a constructor, so it doesn't need one. So anything that has the iterator method name like this is a special case, just like a constructor, that does not need a return type. So all that we need to do is return new list iterator T, and inside of these parentheses, you place this object. And this is going to make an iterator over the current object. Question?
Why would we not put the list iterator in the list iterator class? Why would we do it in the?
Because we need to attach it to a particular object. So when we actually go make the So the list iterator itself can be constructed and take in a list. But if we want to adhere to Java's typical syntax, every collection element that exists has a dot iterator to be able to make it. So we could make a new list iterator and pass it the list as a way to construct it, but we can also embed that logic within the linked list to call the list iterator constructor, passing it this object. In general, when you're making a list, you don't want the user to have full read-write control over that list. So this is another way also to encapsulate that inside of, if you make a list and want to make an iterator for that, then the list iterator, we could actually turn this to be, instead of public, we could make this protected. And now the only way to call this list iterator constructor would now be through the list itself. So it allows you some extra options for the security of your constructors as well. Very good questions, though. So does that make sense for passing this object as the parameter to the list iterator constructor? And this will make an iterator. As we save this, we can see that we go back to our driver and this is now implemented. So from this scope, we call the list iterator method, which calls the list iterator class constructor, which returns us the object of type list iterator. It was generic, but now inside of this scope, we're saying it's double. We want this list to store doubles. All right, this is the level of implementation. I think we're basically where we need to be to assign the first assignment. With the last few minutes of class, I just kind of wanted to open it up to people to say, what is, let's start with thumbs. Feeling like everything together with this linked list, how well do you feel like you understand this put together as a whole to now go modify or to go add functionality to? So I feel like I'm right there with you. Few things that concern me, but for the most part, I'm there. I understand some of it, but I would like some clarification on some other components. I'm lost. We should have a larger conversation somewhere to help me get caught up. All right. This seems to be about where I would expect it to be, especially ahead of an assignment. That assignment is going to be a lot of, I think, what turns these or these into something that hopefully makes a little bit more sense, gives some back and forth. Is there anything from anyone who was in this area? What can I explain over the last couple of minutes of class today that might help push you in the right direction for getting started on an assignment, knowing that the assignment is going to be using this same list interface, make a doubly linked list, a doubly linked list iterator, a circular linked list, and a circular linked list iterator. With the extra credit being, there are going to be a couple other methods that you need to implement in there as well. One of those extra credit methods would be the ability to attach a linked list to another linked list that is a different type. So I want to attach some nodes from a doubly linked list into a singly linked list. So now I now have to go determine, are these nodes the same type? If they aren't, convert them. Yeah.
I just want to clarify. We're modifying this interface to add those.
We're going to implement this interface. So the interface is basically done. But you're going to construct, instead of a singly linked list, you're going to write a doubly linked list.
Okay.
That has, yep, in a different file that has the exact same functionality as the singly linked list, but now there's a next and a previous instead of just a next.
Alright.
For the circular, when you do tail.next, that'll refer back to the head. When you do head.previous, it'll refer back to the tail.
Alright.
And those are the only real changes, but I want to make sure that the changes that you need to make within this to make that work, that you understand this well enough to be able to make those modifications to it. Anything else I can describe on people's way out the door? All right, as soon as I have a moment in my office, I will throw that up. And starting tomorrow, we're going to transition and start talking about computational complexity, one of my favorite topics in the entire computer science curriculum. So I will see you tomorrow for that. I have 2 hours of office hours starting now. If your thumbs were in this area, even if it was in this area, feel free to stop by, get some individual questions answered. I'm happy to clarify anything, work with you for as long as it takes. Doesn't matter to me to get your understanding where you want it to be. Sorry? Yes, it's taught usually fall spring. Yeah, Dr. Sandy's taught that they're in the spring, I'll be teaching them in the fall.
Unless it's changed.
Yeah.
Later.
Yeah.